Hello and welcome to the XP Solutions XP Live webinar. My name is Gavin Fields and I am a Senior Water Resources Engineer here at XP Solutions. Today's webinar title is for Malaysia for Design, Rainfall, Calculator and Hydrology Methods. This webinar will be useful for you whether you are new to designing hydrologic calculations for hydraulic purposes or whether you're refreshing your skills. So for today, the agenda is to go through a bit of an introduction to the hydrology in general and also how it relates specifically to the requirements in Malaysia, getting through physical characteristics, design storms versus historic storm options and how we go about designing or undertaking calculations for those two options and also why we do that. Look at some of the routing methods that are recommended for the Malaysian region. And then definitely get through some results and briefly touch on direct rainfall towards the end. So just briefly about XP Solutions for those who are new to our software, or if you haven't struck us in the past, XP Solutions is a software supplier and we provide solutions for wastewater and stormwater in particular. We have a range of products with our dominant product being the xpswmm product. And that's what I'm going to talk to today. We generate graphical user interfaces and supporting analytical engines to undertake our numerical calculations. Importantly, the calculations do complete solve the complete St. Venant equations, otherwise referred to as the dynamic wave equations, for gradually varied one-dimensional and unsteady flow. And we also have a two-dimensional engine which is a module we call XP2D. So, why is hydrology important? Hydrology is very important in the Malaysian context for agricultural purposes, planning purposes for development, and analysing both local stormwater issues at a street scale, at a residential scale, and also at a regional flooding and flood risk scale. From an engineering perspective, it's always about, typically, understanding the impact of change. What is the impact of converting an undeveloped area into a fully developed environment? The hydrologic cycle is obviously fundamental to hydrology. So we need to obtain our rainfall from the sky, understand how it is conveyed along surfaces into our storages, be they dams or river systems, discharging into groundwater or back out to the ocean or ultimate receiving bays, and the cycle starts again. And from an engineering perspective, managing stormwater definitely means managing our catchments, and understanding our catchments and the various contributors to discharge is very important, but always a catchment is defined by ultimate high points, whether they be at a local scale or at a major geologic or topographic scale for mountain systems versus, for example, a high point in a road. Malaysia is obviously comprises of several island systems, the dominant system to the west and major areas to the east. And there is key topographic elements, particularly to the west, the main areas running from Kuala Lumpur through to the north, and they define how our rainfall systems do propagate, how monsoonal systems propagate out of the South China Sea versus the systems further to the west, but also interact with systems, greater systems even further to the east, I beg your pardon, west towards India. Those monsoonal systems definitely have direct impacts on when major rainfall occurs in Malaysia and how it propagates. This simple map has some of the key areas, key river systems, and no doubt people listening today will have a much better appreciation of these major river systems than I do, but definitely a number of major river systems do exist across Malaysia. And flooding is such an important topic. Now, catchments can vary in size. They can be these local urban systems, or they can be these major catchment areas, sort of as we showed on that previous slide. And rivers distinctly play an important role in shaping our landform, modifying our geographic characteristics from upland areas downstream out to the ocean. Topography itself has a key role, as described. Those mountain systems that run through the centre of the western island of Malaysia has a key role in how these climatic events occur. And we get systems, processes such as orographic rainfall, where warm air rises, cools, loses its moisture in the form of rainfall, and yet behind those mountain systems may often receive little or no rainfall at all. And that is something that can definitely occur at specific times of the year across Malaysia. And again, that mountain ridge can generally be seen here by these major river basins, that there's this distinct separation between the river basins. None of these river systems cross the eastern, the western island of Malaysia. Some general characteristics of some of the major systems can demonstrate that the length of these systems can be quite large, 440 kilometres in length for the Pang River, with a catchment area of 27,000 square kilometres. It's a relatively large catchment. By no means is it the Amazon or the Nile catchment, but respectively speaking, it is still a relatively large system. Interestingly, has some very high variation in topographic elevation, with the top of Mount Tahan being nearly at 2,200 metres above sea level. Certainly where I am here in Australia, there are very few locations that get to that elevation. There would only be one or two catchments in the entire country that would be able to have that kind of change in elevation. The monsoonal rain systems that propagate across Malaysia in the specific times of the year often cause what I would define as slow onset flooding. It's broad in nature, broad spread, saturates catchments, and can result in quite damaging and expansive surface flooding. However, in some parts of our developed areas, for agricultural purposes, we try and hold on to and retain water, whether that be via manual control or pump systems, or these defined topographic systems that can often be required. We want to try and maximise and utilise our supply of rainwater because it has such an important element to our agricultural sectors. That change in hydrology too is very important, and this 3 aerial photos just shows the same location over the last 60 odd years, going from limited development on the left hand side in the mid to late 1950s, development kicking in through the 1980s, and some quite extensive development. Obviously the photography gets better as well, as I took this from last year. And this change in surface catchment details changes in particular infiltration rates and our ability to harvest and utilise our water supplies. Final types of flooding that we can try and observe and try and deal with from a hydrologic perspective comprise of flash flooding, rapid onset floods, and also slow onset floods. They're those monsoonal systems. And these systems can occur either rapidly or over long periods of time. And of course many factors affect whether or not any given location is prone or subject to these 3 types of rainfall systems. Obviously from a hydrology perspective, we can make these direct observations to how catchments respond to runoff, and that observation is typically made in our river systems. We can watch how from the time that the rainfall occurs, what kind of lag we have until we observe our peak discharge rates, and then of course how long it takes for that catchment to recede or dry out. Also the interface with ongoing base flow from our groundwater systems. Now some river systems, this is just an example, this one's one that I'm aware of in Queensland. I apologise, this one's not in Malaysia, but the Barron River, I'm sure there are rivers in Malaysia that exhibit the same characteristics. Can go from relatively dry systems to having some rainfall and having a rapid change to having some quite extreme runoff. And this can occur very rapidly in some of our catchments. It has an impact on warning us, our populations downstream, about the impacts of flooding. So from a numerical perspective, and today's topic is to try and get to some of the practical applications of hydrology, is obviously the assessment that we have rainfall, we subtract our losses and derive our runoff. Now, in certain parts of the world, snowmelt is an element that kicks in that is not that dominant. To my knowledge, in Malaysia, likewise, it's not at all dominant here in Australia, but in different parts of Asia that are connected to the Himalayas, in particular, or Europe and parts of North America, then snowmelt can be a contributing factor. And our losses typically take the form of evaporation or evapotranspiration, taking in vegetative losses as well, groundwater infiltration, and depression storage, those filling up of ponds or dams or undulations in the surface. And of course, the result of that assessment is to derive a hydrograph, which can inform us about peak discharge rates, but also, very importantly, the volume of a particular storm event, whether it be a design storm event or a historical event that's being back-modelled. So, design storms and historic storms. Design storms are a tool that is supplied to the engineering fraternity to allow us to predict based on a retrospective view of actual rainfall events for design purposes. Now, this is very important because on most catchments we don't have enough information to actually properly calibrate any given catchment. If we're able to calibrate our catchments, we realistically would not require design storms. We would be able to run historic storms in all situations, and that would be by far and away potentially a more appropriate way of modelling our systems. But again, in the absence of detailed information, design storms are the industry accepted replacement. Now, at times, if you're modelling a large river system in Malaysia, then definitely you would be interested in understanding or trying to demonstrate the performance of a historic storm numerically, and that gives us the ability to justify the parameters that are fed into our calculations relative to how the real world performs. With the design storms, we need to get intensity information, rainfall intensity, and I'll show you a nice utility that we have inside xpswmm and for the Malaysian region, which is our intensity frequency calculator. It's a very useful tool to get you quickly into your modelling. I need to assess a range of storm durations. This sort of approach, this design storm approach, is not an equivalent to the rational method. And I'll talk a bit about the rational method shortly, but it's not a situation of modelling simply one storm duration. We need to assess a number of durations. And the temporal patterns do come from the MSMA2 documentation, which is a great reference manual for the Malaysian region, and I hope that everyone either has a copy or is familiar with that document. I'm going to go into the software, and I'll show you inside our software how the software deals with that Malaysian information. So on this node 1, this is I'm just using this as a representative catchment, and I have just applied a simple 1 hectare area to the catchment, but inside the interface I have some rainfall information and a variety of different locations. We can create locations at anywhere across Malaysia, but if I just create a new one, I'll call this JPS. Okay, and I'm going to hit add. I'll edit this, go into this particular dialog box, and I have an IFD calculator. This is specific for Malaysia, and this IFD button, I can select the type of ARI for the study, select my my location. So if I were to go to Selangor, I can select JPS Ampang, nominate a ARI and a duration event, and press the calculate button, and that will define the average rainfall intensity or depth of rainfall, and it's exactly the same because it's 60 minutes in this example. But if I were to change this, I could recalculate for 25 minutes, and it would give me that variant detail. So that's a very useful utility for our Malaysian clients. I'll just change that back to 60 for this example. And that information gets back populated here, and we would just apply the temporal pattern for that 60-minute storm from the MSMA2 guidelines, and I'll show you one of those a little later on. Back into the slide. So historic storms can take observed rainfall data, and if you can get information from either the Bureau of Meteorology or your local authorities in Malaysia, we can take this information to use it for flood forecasting purposes, thorough calibration, and once you've undertaken a calibration, you definitely want to validate or verify that model with another historic storm event. And one question that was posed to me recently was from the Malaysian region was, what is the accuracy of the rainfall data sets that we need to have to undertake these historic studies? We definitely need sub-daily time steps. Ideally, you would want to obtain the raw rainfall data to allow an appropriate study to be undertaken. Taking daily values simply distorts your ability to analyse a catchment, because you'll have to assume the rainfall occurred consistently over the day, whereas we know that rainfall spikes in sometimes very brief periods, either 5 or 30-minute periods. So daily historic data is inadequate, and if you're able to procure sub-daily values, or again that raw information, when did the rain gauge tell us that it received a millimetre of rain, that would be a much better data set to analyse. We can feed in those rainfall values, apply infiltration procedures to that to define discharge from our catchments. And so what I've done here with a real rainfall set is applied some ongoing losses, and we can see that because of the potential for catchment infiltration, we don't actually have any runoff in response to these small events. But when we get into these larger events, we see spikes in our runoff record. And so obviously if in the absence of design information, which fortunately Malaysia actually does have a pretty good data set of, you could look at some statistics to back derive your design events, looking at the probabilities of events occurring over time by doing an assessment of your rainfall records. But again, the fact that we have design data in Malaysia makes this not a common task. Just quickly back on storage and losses. Another loss that is sometimes accounted for is interception. Now, interception is most regularly considered in an urban context to be rainwater harvesting. So a rainwater tank is actually an interception device. It takes that rainfall from your roof areas, stores it, and hopefully it's used for beneficial purposes post-storm event, be that for landscape irrigation, toilet flushing, or potentially laundry washing. Evapotranspiration from the surface plus your vegetation, again infiltration we spoke about before. But these factors all need to be considered in your hydrologic calculations. Inside our software we actually have 4 dominant loss methods. However, for the Malaysian context, only 2 of those really stand out as being appropriate as per your guidelines. The first of those is Horton's method, and it can be adapted to be a continuous loss method if you were trying to run a long duration time series, for example a year's worth of rainfall under historic analysis, or uniform losses, which are most commonly applied for design storm modelling. The common option out of the 3 uniform loss types is the initial and continuing loss method. But we do have GreenAMP and the soil conservation service methods, which are used around different parts of the world, particularly America. In defining or deriving our runoff, we run through a process of taking the rainfall hydrograph, which is either the design storm temporal pattern from the MSMA2 guidelines, multiplying that by the IFD value that we may have obtained from the calculator inside xpswmm. Subtract that loss model. That initial continuing loss would be the most appropriate way. Define a excess hydrograph. Multiply that by our catchment area to generate our hydrograph for assessment. Now inside the software we actually have about 23 or 24 different hydrology methods, but the three that do stand out for the Malaysian context are the rational method, Laurenson's method, which is referred to by a number of people in the industry as rafts, but the actual equations behind that is Laurenson's method, and also time area. From my perspective, I would always pick Laurenson's method. It is by far the more advanced method of these three, and it is definitely one of the recommended methods out of the MSMA2 guidelines for application in Malaysia. Now the rational method does have a number of limitations, and that's something that people do need to be aware of from a hydrology perspective, and that is that it is not really valid beyond any storage system, whether that be a detention basin, a lake or a dam. And so that can be quite a difficult element to factor in. And if you're working in new development areas that have large-scale rainwater harvesting systems, that too would be another reason to not consider the rational method valid for that kind of application. Another limitation is on catchment area, and the MSMA2 guidelines state that the rational method is to be limited to a catchment area of 80 hectares. Other parts of the world do have some higher limits than that. However, here in Australia, our main stormwater guideline is being updated, and it will limit engineers in this region of the world to only allow you to model 2 residential allotments using the rational method. Now that's a very small area. That could be 800 square metres. So we're not talking in hectares anymore, we're talking in hundreds of square metres as a limit to the rational method. So that has some far-reaching consequences. Of course, the other key limitation is it only tells us a peak discharge rate based on the concept of the time of concentration, which means that it's not suitable to size detention systems. Now there are some equations to try and force the application of the rational method to size storage devices, but they're by no means rigorous relative to the data that we have available in terms of our design storm information or our ability to undertake calculations very rapidly inside computer packages such as xpswmm. Some key parameters that we need to deal with in order of importance: catchment area, that is the most dominant parameter that we need to play with. The rainfall, again using the temporal patterns and the IFD information. We have other parameters that then support Laurenson's method in particular, which are catchment slope, the catchment roughness. Some methods, but not Laurenson's method, use catchment width or a length. So if you were trying to undertake a Bransby-Williams style calculation to derive a time of concentration for a catchment, if you felt that was appropriate for you, then by all means you would definitely need the catchment width in that equation. So from the total area and the width, we can imply the length. And then an understanding of the land use characteristics, which helps us define our infiltration or our losses. That's just a quick review back on that IFD calculator, same location, that JPS umpang, which shows with a temporal pattern applied. That's the 60-minute pattern, and how that would be applied to the software. And so from all of that background information, what is it that we're trying to achieve? Why are we interested in running these calculations? And of course it's to derive these peak flows and volumes relative to our rainfall input. And so these 3 shots that I have at the bottom of the screen here, one shows that long duration analysis. You know, that's a month's worth of rainfall versus a specific rainfall event in the middle, or a design storm on the right-hand side. And each have distinctly different approaches to them. But the important thing is to be able to analyse all of these if and as required. Just for background information, we do have, again, those many hydrology methods in addition to those three that I talked about before. But just focusing on the rational method quickly, it is derived based on this concept of a critical time of concentration, and most people are very happy with it and understanding it. I think it's a very good rule of thumb, but it is by no means the be-all and end-all of a hydrology calculation set. And by no means would I expect anyone to try and, unfortunately, use the word calibrate any other calculation back to the rational method. That would be an improper approach. The only thing that we can calibrate to is real-world data. How does a river system perform in the real world versus our calculations? Now, you could try and calibrate the rational method to the real world. You could also try and calibrate Laurenson's method to the real world. And your approach would be slightly different in both the examples, but with the ability to get more information out of a hydrology method, which would give you not only just the peak discharge rate in the river system, but also the total volume that contributed behind that peak volume, peak flow rate. This Laurenson's or rafts hydrology is very common here in Australia, but it is also very common in Malaysia, developed by Dr. Laurenson, and it runs on this principle where any individual catchment is broken up into 10 sub-elements, routed internally, and based on a storage equation. And that storage equation is a function of catchment area, the roughness of the catchment, an urbanisation factor, so that's a function of the fraction impervious, and roughness details. And so this is the core equation, where storage is a function of this B parameter, and B has a bigger equation below it, multiplied by flow, and then a non-linear exponent. And so the reason we need to use a program for this is because at the first time step we don't know S, and we also do not know Q, and so we need to apply an iterative solution to the system to derive our results. But the B parameter, the B equation, is actually well defined. It's all based on physical parameters, although we do have a Bx value at the back there, which is a multiplication factor for gauged catchments if we need to make a slight adjustment to factor in some of the parameters that occur in the real world that can't be factored into what is relatively a simple equation. Time area is another popular method, I understand, in Malaysia, although again I would likely not personally try and apply this in Malaysia. I think it has a few limitations on it in terms of particularly larger catchments, but also not necessarily flexible enough relative to the demands for detention basin calculations. So running a more rigorous hydrograph method like Laurenson's method is not only quicker, but makes assessment more rigorous. When we take any given site and start with a low or limited impervious component, and then compare that to a fully developed site, we get these substantial changes in the shape of our hydrographs. So the curve on the left-hand side there is a nice smooth curve from a zero impervious site, and the curve on the right-hand side is showing a 60% impervious site using Laurenson's method against a temporal pattern, a design storm. The area underneath the curve on the right-hand side is greater than the area underneath the curve on the left-hand side, so we've got more water as well, not only a much bigger peak discharge rate, so we're going from just shy of 350 litres per second to up near 550 litres per second in response to development. And hydraulically, you would then need to look at potential solutions to try and mitigate that increasing discharge. And at times, if you have a volume-controlled catchment, you may need to look at clever ways to store that water and hopefully limit it in getting down to the river system if you have, again, a volume-controlled river system. So I've just taken some a snapshot of the Malaysian temporal patterns, and so this shows a range of the patterns from the 5 minutes through to the 120 minute. This does come from the MSMA2 guidelines. A bit hard to see with the overlap, but you'll get a perception. This is the temporal patterns multiplied by their respective IFD values to put them at a scale. And when we apply these with Laurenson's method inside the software, we can generate these discharge curves. And for a simple catchment, I think this is my 1 hectare example. For a undeveloped catchment, a 0% impervious catchment, my critical storm is actually the 60-minute event. Now, if we were to convert this to a developed case, then I would expect to see that possibly the 15-minute or maybe the 30-minute pattern might actually be the dominant pattern in response to the change in fraction impervious. I'll just jump back to the software just to give you an indication of how long it takes to run this model. So obviously it's only a simple model, only the one node at the moment. If I hit solve, I'm running these 6 storms, and it is as quick as that. For me to prepare this off limited information, it takes me almost no time to obtain some rapid results. There's that same set of results from the software, and not only can we obtain for these multiple storms peak discharge, but I can look at rainfall totals, the impacts of infiltration and other parameters, and I can also isolate down and just look at one storm if I wish for reporting purposes. It's very important to be able to get this information across to not only our clients as consultants or interested individuals at a state government or assessment level. So very, very quick to model inside our interface with limited information. What is becoming really popular in certain parts of the world is this concept of direct rainfall, and that concept relies on a 2D model rather than a point 1D model like that simple one node that I showed a second ago. It means we need to have good surface information, and unfortunately I'm aware that surface data is at times limited in the Malaysian region, but over time no doubt the capture of completion of aerial survey, obtaining LiDAR information will improve and be expanded, and all you need to do in a model then is bring that surface terrain information into the software, draw a polygon out to the catchment extents, and tell it to rain, and apply your design storm to a polygon, and storm data will then distribute itself, find the low points, and accumulate as it would, hopefully, in the real world. There are some limits to it in that you do need to have a relatively fine terrain data set. That's our biggest limitation in the short term. Secondarily, you need to understand your land use, and then also the impact of surface roughness elements. And those surface roughness elements could be in the form of a building, because typically when we have our aerial survey, we remove or filter out buildings from the surface, and so water would inherently try and flow through where a building is, and of course hopefully your buildings are generally impervious at their lower components. If they have a concrete slab, or if they're an elevated building, well maybe that's not so important if they're a pole home, but understanding the impact of buildings and also fences, particularly blockwork fences, becomes a difficulty for these models. But here in Australia and America and other parts of Europe, direct rainfall is really taking off to undertake very large area studies respectively quickly, although these models can take sometimes hours, sometimes days, and I have heard of several examples where they can actually take weeks of computer time to run. And so this is just a simple example of saying, well, here's some terrain inside our interface, and this is where I expect the catchment boundaries to be. So this polygon here is where I'm saying the cloud is effectively, and that the software would then define where the water goes from there. But look, that's possibly something that will be a little bit difficult for the Malaysian market until LiDAR information becomes more readily available, or if it can be procured on a project-by-project basis, then so be it. But look, that generally brings me to the end of today's session. A relatively rapid overview of hydrology. I definitely just wanted to demonstrate that the tools there are available to the Malaysian market for using the design rainfall calculator. It's very simple to use. Pick your location and apply that to the temporal patterns. Those temporal patterns are all supplied and developed by Lestari software. They do a great job looking after the Malaysian market, and or get in contact with us here at XP Solutions or at Lestari software. Again, I'd like to thank you all for your attendance today, and hope to hear from you soon.